Welcome to your Introduction to Dynamics. In our first unit, called Kinematics, we studied motion. Motion not including the forces that were causing that motion. In the second unit, in Dynamics, we're flipping over to studying the forces side of things. Now we're still going to study the relationship between force and motion, or force and change in motion, but we're going to focus more on the force side of things. So first of all, dynamics is the study of forces. And you've probably learned back in elementary school that a force is a push or a pull, as simple as that. And that's really the definition that we're going to hang on to for now. Now, if you talk to someone who's an expert in physics, they might tell you that it's a little bit more complicated than that there are certain particles that are force carrier particles called bosons, but we are not going to go that far. We are first just going to start with the simple definition of a force being a push or a pull. That definition works for now because you've experienced that and you know what we're talking about. So we're going to talk about a bunch of different kinds of forces. We're going to talk about the force of gravity, we're going to talk about the force of friction, the normal force, and tension. Now let me show you a few ways those things can be applied. The force of gravity is the force that causes two masses to be attracted to one another. In this case, the golf ball to the earth. Friction is a force that resists motion. Specifically, it resists two surfaces sliding past each other. It's why things slow down and stop. Now, the normal force is a bit of a strange one. I've written down that it's the support force a surface exerts on an object. So let's think about this dumbbell resting in my hands. So my hands are a surface that are supporting this dumbbell. Gravity wants to pull this dumbbell down, and it would if my hands weren't here supporting it. So the force of gravity is pulling this dumbbell down, but my hands are exerting an opposite force, pushing up against gravity. So my hands are exerting what is called the normal force. So the normal force is a support force. My hands are supporting this dumbbell against gravity. The support force exerted, and it's always perpendicular to the surface. So if my hands are parallel to the ground like this, parallel to the floor, then the normal force is going to be perpendicular to the floor. It's pointing straight upward. But if I tilted my hands, I don't want to because I'm going to drop this on my computer, but if I tilted my hands, hey, like this, then the support force that's being exerted on this thing is not any longer perfectly straight down, or perfectly straight up. Now it's going to be pushing off at an angle like this. It's perpendicular to the surface. And that's why it's called the normal force. Usually in English now, we consider the word normal to mean regular or ordinary. But in math and science, the word normal means perpendicular. And so the normal force is not the everyday force or the ordinary force. It's the perpendicular force. Okay, so remember that. Normal means perpendicular. And here's the final force. Tension is a pulling force. It's just that pulling force is exerted through a rope, a chain, or some object like that. So these are the four main forces that we're going to come across in this unit on dynamics. These are not all the forces that are possible, but this is a good start to categories of forces that we can study. So we're going to move on to some history of force, as well as talking about Newton's laws.
Now, Aristotle believed that a force was required to keep something in motion. So, in order to keep this tractor moving, I will need to keep pushing on it. And once I stop pushing on it, it's going to stop. Now, that maybe seems like it makes sense, but it won't stop the moment I let go. It'll keep going for a bit. I stopped pushing it and it kept moving. So Aristotle wasn't quite right, or maybe he just didn't explain himself quite right. So when I stop exerting a force, it keeps moving. But we know that it eventually stops because friction will stop it. There's an opposing force that's going to cause it to slow down and stop. So he wasn't quite right. Objects do continue moving when you stop pushing them, but eventually they're going to stop because there's another force acting on them.
So that brings us to an advance in thinking with Sir Isaac Newton. Now you might have heard of Newton's 3 laws of motion, and that's what we're going to go through right now. Newton's first law is called the law of inertia, and it says that objects at rest tend to stay at rest, and objects in motion will stay in a continuous state of motion, moving in a straight line, unless an external force is applied to them. And that means a force that's not contained within the object itself. So if you are driving in a car and inside and you pop it into neutral, so now you're just coasting, you're going to continue moving in a straight line even if the people in the car start pushing on the inside of the car. You're exerting a force on the car, but not an external force. So that force is not going to change the motion of the car at all. So an external force is applied that will change the motion of the object. That's called the law of inertia. Inertia is just the tendency of an object to continue doing what it was doing, staying at rest, moving in a straight line, whatever it was. So that's called constant velocity. So I just wrote down net force. So net means total, and in this case we mean unbalanced total force. So a net force would be an unbalanced external force acting on an object. Okay, so net force just means the total or the vector sum of all forces. And by vector sum, we mean you need to take direction into account. So if two people are pushing on each other, this direction, one with 10 newtons and the other with 10 newtons the other way, it's not 20 newtons of force, it's a total of 0. So we have to add up the vectors. Yes, if an object in the middle was being squished by the two of them, it would get squished by 10 newtons on one side and 10 newtons on the other side, but the total force is really still going to be 0 newtons because they're the same and opposite directions. So when all forces are balanced, like the example I just gave, you get F net equals 0 right here. So that means that the total force acting on an object is 0 newtons. This occurs when an object is at rest, not moving. So if nothing is pushing on something, it's just going to sit there. So when an object is at rest, we get F net equals 0, or when an object is moving with constant velocity. Both of those circumstances will give you a net force of 0. Remember that constant velocity means that there isn't an unbalanced force acting on an object. Okay? So if an object was moving this direction, and then two equal forces started acting on it in two different directions. So let's say something is moving this way, and then you get somebody ready to push it this direction, and another person ready to push it from this direction, and they push with the same amount of force, it's still going to continue moving in the same direction. Okay? An unbalanced force would be required to change its motion. So let's take a little look at this box over here. Calculating the net force on this box is doing the vector sum, or doing vector addition, for these two force vectors. So they're opposite directions, so we can't just go 7 plus 5 is 12. We have to go 7 to the right, and 5 to the left is a total of 2 to the right. Okay, 2 to the right. So this is 7 to the right, plus 5 to the left equals 2 newtons, we're talking about, to the right. We can also write this as subtraction, because left is just negative right, right? It's the opposite direction, and so it's the negative version of the right direction. Okay, so this could also just be 7 newtons minus 5 newtons when we are saying that to the right is the positive direction and to the left is the negative direction. gives us the same thing. Now let's take a look at this second one here. We've got 3 newtons pushing to the right. We've got 6 newtons pushing to the left. We've got 2 newtons pushing down, and we've got 2 newtons pushing up. And so when we're talking about net force, we have to look at the vectors that are acting in the same plane. And so by the same plane, I mean this 2 newtons and this 2 newtons, they're both acting in the up and down direction. Okay? So we can consider 2 newtons up to be the same thing as negative 2 newtons down. Right? So we can just flip these two, we can interchange their directions because they're related by a negative sign. Same thing with the left and right. The 3 newtons to the right is just negative 3 newtons left. And so we can add up the left and right directions because they're in the same plane. And so in this particular example, the 2 newtons over here and the 2 newtons over here, they're just going to cancel each other out. If you push down on something with 2 newtons and you push upward on it with 2 newtons, that net force is just 0, right? Net force is just the sum of all forces acting on an object, but in this case we're talking about acting in a certain plane. And so the up and down, or the y forces, they cancel each other out. But the x forces, or the horizontal ones, they are not the same. They don't cancel each other out. And so we can see that if you push with 6 newtons to the left and you push with 3 newtons to the right, then you're going to end up with a total of 3 newtons to the left. Okay, and so our total net force is going to be 3 newtons to the left. Often we are not going to talk about left and right and up and down we will, but left and right, we won't really talk about that because it's easier and a little bit clearer to talk about north, south, east, and west. And so left, in this case, would be west, right? And right would be east. So we'll often use compass directions as kind of our standard directions. So Newton's first law is called the law of inertia because inertia is the tendency of objects to maintain a constant state of motion. The tendency to resist changes in motion is another way of saying it. And so an object with a lot of inertia, it's really difficult to change its motion. So I always think of a freight train. So a train is so enormous and so heavy that if you want to stop the train, you have to apply the brakes way early because it's just so difficult to change its motion because it's really, really heavy. And that's really what it comes down to. Objects with a lot of inertia are objects that have a lot of mass. So we're putting together a picture here about force and its relationship with motion. So Newton's first law is the first piece, and that has a couple ideas built into it as well. There's the idea of inertia, that things tend to keep doing what they were doing unless there's an external force applied. And that second idea is the external force, is the net force. And we can talk about net force using equations, so adding up the forces in 2 different directions. We can also use pictures, or what we would call free body diagrams. So it's called a free body diagram because we are kind of severing an object's ties to whatever is around it and just looking at that object itself. So if we look at the examples on the page here, we have a skydiver, first of all, falling through the air at a constant velocity. And we're supposed to draw all of the forces acting on that skydiver. Now, that skydiver is not attached to anything else, right? And so it's not hard to think of it as a free body. But the bucket below, it is attached to a rope, okay? And that rope is pulling upward on it. The rope is not considered part of the bucket in a free body diagram. We're looking at just the bucket. It's free. It's not attached to anything else. That's what free body means. So we're going to draw the forces, just the vectors themselves, just the arrows, that show what direction forces are acting on these bodies or on these objects. Now when you draw a free body diagram, ideally you would draw the vectors with sizes that are relative to each other. And so when this says a skydiver falls downward through the air at a constant velocity is kind of a key word that's going to pop up quite frequently. And we said that constant velocity is one of those situations where all the forces are balanced out. When there's unbalanced force, then you get acceleration. You get speeding up or slowing down or changing direction. But when there's constant velocity, that's just consistent motion. And so that's just following the law of inertia. So this skydiver falling at a constant velocity means that the force that's pulling them down is the same as the force that's pulling them up. They've hit terminal velocity, that's called. So when we draw these vectors, we draw a downward vector for the force of gravity. We're going to label it. And we're going to draw an upward vector for the force of drag, or air resistance. So the force of drag is the general term, but you can have drag when traveling through any fluid, through air, through water, through jello, whatever. So we're going to call this Fd, or the force of drag. Now, if you use a lowercase d, that's fine. It's just that later on, we're going to have a formula that uses capital D. Okay, so I don't really care about that. But notice that I've drawn these two arrows pretty much the same size. That's because our forces, our up and down forces, should be balanced out. And so our arrows should be relatively the same size. The second one, a rope is lifting a bucket at a constant speed. Again, we notice constant speed. Constant speed means no acceleration, which means all the forces are balanced out. And so we have an upward pull from the rope. We can just call that either the applied force, so someone is applying that force, and so we can just call it applied force, or FA. We can also call it the force of tension, because any force that's being applied through a rope or a chain or wire or something like that can be called a tension force. So I am going to call this the force of tension, Ft. But there's a couple different ways of writing this. We could also write just big T. That also would stand for the force of tension. Now this happens because there's also another force that we often come across called the force of thrust. And that's really any engine exerts a force of thrust. And so this, Ft, would also stand for the force of thrust. And so just so we don't get mixed up, most often we're going to just write big T for the force of tension. Okay? But the force of tension pulling up on this bucket is balanced out with a downward force. That's what constant speed must mean. And so the downward force should be about equal size. And the downward force is going to be the force of gravity, Fg. And so this bucket is experiencing equilibrium. It's experiencing a balanced set of forces, and so it's going to move at a constant speed.